Okay, I think that was the signal. Great. All right, so the title is quite ominous. I stole that from a Woody Allen movie. Meant something else originally. But I want to start our story here with Alan Turing. And if you've studied computer science, then you know exactly who that is. The founder of computer science. In the 30s, he wrote a master thesis, right? What later would become the Turing machine. Then, of course, he helped the Allies crack the Enigma code. That's something that you probably remember. And then in 1950, he writes a paper. He's in Manchester, and he writes a paper. And if you haven't caught on already, that this is not really Alan Turing, right? Because that's AI generated. This is Midjourney 5. But he writes this paper, and he sets the foundation for machine intelligence. And he devises a test, the Turing test. Later, it would be known as the Turing test. And the Turing test is very simple. You have a human questioner, and there are two participants. One of those is a computer, and the other one is another human. Now, it is said you pass the Turing test if you can convince the human questioner that you're not the computer. So that sets the foundation. And then throughout the 50s, artificial intelligence, or just computer intelligence, as it is called, is gaining steam. And so in 56, we have the Dartmouth workshop. And so that's a famous bunch of people. If you dabbled in computer science, John McCarthy, Marvin Minsky, those are quite well-known names. They both went on to win the Turing Award, of course, named after Turing, right? The Fields Medal of Computer Science. But John McCarthy actually coins the term artificial intelligence. And if you ever went to MIT, there's a whole section, Marvin Minsky and his crazy ideas. But they went on and they started building prototypes and proof of concepts and demos. And the fascinating thing is they attracted a lot of money. So a lot of money came in, which ultimately led to this. AI winters. So some people claim there were 3 AI winters, some people say there were 2. Depending the literature you follow. But after they attracted a lot of money, in around 66 to 1980s, there was the first AI winter. And the challenge that they had is they could never make the models, the proof of concepts, the demos scale beyond what they intended to do. So they were stuck, essentially. And I want to give you a very simple explanation why they were stuck. So this is a 9. We can clearly recognize this as a 9. But for a computer to recognize this as a 9 with reason and logic and mathematical models, you need to describe this. We can describe it. It's an oval shape, has a certain width, right? It arches down, there is sort of a half curve. What happens if we tilt this by 45 degrees? Already it's hard to discover that this is a 9 because it's 45 degrees turned. If we use the same rules that we applied for the original 9, a computer will not be able to identify this. It gets better, right? If you change the font, now it's completely different. Or even if you underline it, it's a different story. So they tried to create models of the world that they know, so they could reason and use logic. And with the complexity, this simply did not work with the computing power that we had in the 60s and 70s and 80s. But things started to look better, right? As soon as we sort of moved into the 90s, Deep Blue defeated Kasparov, and this actually was a brute force attempt, right? So this was just throwing CPU cycles at a math problem. That's how Garry Kasparov got defeated. And Deep Blue is about 100 million times faster than the first chess computer. So it was, just brute force. But more interestingly is the DARPA challenges, the series of DARPA challenges that started in the mid-2000s. And they started to use machine learning. So they used machine learning to figure out, what is the probability I can drive on this road through the desert? So that's a big first use when this sort of came up. Of course, we have used machine learning before that, but that was a very public demonstration. And then around 2009, Google starts to experiment with stuff, and they replaced their NLP engine, and I think this is in Android or elsewhere, with neural networks. And the experiment, or what I want to point out, the fun one here, is in 2012. So Andrew Ng and Jeff Dean, they create a huge neural network model, 16,000 microprocessors, and they feed that model 10 million pictures, screen captures, randomly from YouTube videos. I mean, this is Google, so they had access to all the data. So just at random. And what they found is that there are a lot of cats on YouTube. And the model was able to distinguish between cat and human when you play back the data. So it's a breakthrough in itself, right? It sounds silly, right? 13 years ago, no, can I do math? 11 years ago. But the breakthrough, and the reason we have generative AI is really deep learning. And so this trio here is famous. But Yann LeCun, I think he's actually French, could be wrong. Bengio, and of course Hinton. And Hinton is very vocal. Actually, they're all quite vocal about this topic now. It's interesting. But in 2015, they released their paper on backpropagation. And backpropagation, I tried to summarize this in one sentence, is nothing more than a neural network that can reconfigure itself based on input and output. Maybe I'll have something better because I have a short clip on how this all works. But I want to do a quick AI classification because we started with classic AI. Right? Reason, logic, try and describe the world. And we went on to data. And I have to just make one thing clear. Do we have any data scientists? Did I ask? Yeah, we have one. No, we have a couple. So, right, machine learning just does not work without data. Right? It's a pretty clear case. And that's why data science is the foundation. It's so fundamentally important. And I try and carry that message that we really need to take care of our data if you want to be serious about this. But then, of course, we have machine learning. And machine learning by itself is nothing new. We've been doing it for 20 years, more. And, we have sort of the various models, right? So I have to turn around now. The clustering is sort of your Netflix recommendation. The classification is your spam filter. And the regression is, estimating what your house would be worth in a couple of years. So that's just machine learning that we've been doing for 20 years. New is this, right? Deep learning. And these models, you can actually use data that is labeled, supervised, or you can use unsupervised data. You can do reinforcement learning with semi-supervised and so forth. So there's a variation in how you can use your data. Very quickly, I just want to describe what is different now with neural networks and with deep learning. At the beginning, with classic AI, I tried to show you that this model is too complex, right? Trying to describe the world. So with AI, or with deep learning, we turn this around, right? And we're saying, okay, instead of trying to figure out which one is a 9, we take those 9s, and we put them through a neural network with multiple layers and that have weights and biases in each neuron. So we trade that, and hopefully the probability ends up that this is actually a 9 that we feed in. So I have a 2-minute clip, and I hope we can play this because it has sound, because this explains it really, really, really well.
As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together?
I don't think we have to
say. Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1.
It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number.
So all of these 784 neurons make up the first layer
that
of our
neuron
network.
is active. That's the activation of that neuron. So, you take the whole bitmap.
Now jumping over
you
to the
start
last
feeding
layer,
it into
this has
the
10
neural
neurons,
network. This one
each
has two
representing one of
layers.
the digits. The activation
And
in
it has
these
two
neurons,
layers
again, some number that's
because
between
it
0 and
fit
1,
on the page.
represents
That's
how
what he
much the
explains in
system
videos,
thinks
because
that
in
a
reality
given
this would
image
have many more
corresponds with a
layers,
given digit.
and it would be much bigger.
There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure
so
in just
it
a moment.
explains why it has 2
And 16?
layers. In reality,
Well, that was just a nice number to fit on the
this is
screen.
actually much
In
bigger.
practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next
What he
layer.
says is, okay, if
And of course, the
we
heart of the
bring in a
network as an
bitmap,
information processing mechanism comes
in
down
one
to
layer,
exactly
neurons
how
will fire,
those activations from
and
one layer bring about activations
these will
in the
trigger
next layer.
neurons in the
It's meant to
second
be
layer, and
loosely
then it will
analogous
come
to how in
and
biological
calculate the
networks of
probability
neurons,
in the
some
last
groups of
layer of whether
neurons
this was a
firing
9 or not,
cause certain others to fire.
or a 2 in that
Now,
case.
the network I'm showing here has
And
already
what
been
is
trained to
quite
recognize
obvious is
digits.
that,
And let me show you what I
similar
mean by that.
neurons
it means
fire
if you
in similar
feed
ways,
an
so
image,
in patterns,
lighting up all
which is essentially what our
784
brain
neurons
does,
of the
or
input layer,
similar to our
according
brain.
to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the
and
next layer,
this whole
which
model
causes
is
some pattern in the one after
probabilistic.
it,
So
which
at the
finally
end,
gives some pattern in
we
the
don't
output
have
layer.
a
And
Boolean.
the brightest
It's not
neuron
true or
of that
false.
output layer
It's
is
a
the
number,
network's
how
choice,
probable
so to
is
speak, for what digit this
9
image
or a 4
represents.
or any other digit. Yeah, so he explains it much better. That's why I wanted to play this. But I think we are at the end now of this. Okay. So I want to quickly talk about how is actually AI content generated now. And this is, I looked at this in depth a bit, and I can tell you it's pure math. It's very complicated. So I tried to come up with a way in explaining this in simple terms, because I was lost in the math. I could not follow. But the first thing you already know, you need data. You need lots of data. And I'm talking here about the text-to-image model, so this is not a large language model. This is actually stable diffusion, if you know that. You need lots of data, lots of pictures, and you need to have labeled pictures. So as an example, this is New York. The year is maybe 2014. It points in a certain direction. You can name the buildings. This is New York as well, but this is 1800s, right? Maybe Lower East Side. And this is also New York, but it's Midtown. Maybe late 30s, early 40s. This is a Matisse. Very different. You can label this. Actually, there's a name for this painting. I forgot it. But it's a Matisse in his later years. Now, here's another Matisse. That's a Matisse in his earlier years. That's the Impressionist era of Matisse. If you label all this data and you start to feed your neural network, and you go through this process of the deep learning, when you then, the deep learning first, what it does, it creates this latent space. And the latent space is essentially a multidimensional structure. I can't draw it because it's multidimensional, but it takes features from these pictures based on the labels and puts them in clusters in this memory structure. And when you then prompt the model and you say, I want something about New York, it goes into latent space and it takes features from that New York cluster out and tries to create a model. And when we then ask, okay, show me New York by Matisse, we get something like this. And if we ask, okay, but now I want the Impressionist era, we get something very different. Is it Matisse? I don't know. Is it New York? Maybe. But that's how these pictures are being generated. Features of different images. Large language models, right? They use transformers. We saw this yesterday, right? This is Google came up with this in 2017. They have a big advantage now because they can train in parallel. That makes them much faster. But it also has another development that I want to go into. And that is scale. If you think about the large language models, and if you go back to the 2-minute clip that had no sound, if you go back to that, the neural network in that 2-minute clip was about 1,600 parameters. Right? It had, the number of neurons multiplied by biases and weights, about 1,600 parameters. Now, if you think about the first version, GPT, this was 1 year after the Transformers paper came out. The first version of GPT, 117 million parameters. It's okay, we can do that. The second version, already 1.5 billion parameters. They ran this on 256 NVIDIA Tesla V100 cards. So we're talking 256 computers running for a whole week to train this model. Huge energy consumption. But it gets better. GPT-3, 175 billion parameters. It took the electricity of 120 households over a year to train this model. Think about that. And that should give you sort of a sense of scalability, because these models, they don't scale forever. GPT-4, we don't know. Last week there was a tweet. Somebody claimed that GPT-4 is actually 8 models instead of 1. We don't know for sure, but it does make some sense. But Huawei has a model with 1 trillion parameters. So how much electricity is that? And there is a scalability issue here, clearly. And at the top end, it's an arms race. It's an arms race between big tech, right? The Googles, the Microsofts, and so forth. And at the lower end, there are new ideas. I'm going to touch on those briefly. So I have to speed it up a bit, but where are we on that intelligence spectrum? We are still here. Narrow intelligence. Because all these models, the generative models, they can just do one thing. Right? They can create an image, they can translate text. The next step up, of course, is AGI. Right? This is multi-model. So these systems can do many different things. We expect those to be at our level of intelligence. That's why it's general intelligence. And then, of course, superintelligence is the dystopian future. Right? That's the Terminator scenario. That's what we've seen in science fiction movies and novels over the last 50 years. We're not there yet. Right? And we may never get there. Okay, now I want to do a quick side story because my point was to try and tell you this AI development is 70 years in the making. So this is not something that just happened. And for me, when I looked at this development, it reminded me of something else I've seen. So this is Douglas Engelbart, famous Douglas Engelbart, 1969, inventor of the computer mouse. He gave the mother of all demos. Actually, it's not Douglas Engelbart. It's AI generated because I couldn't find a picture of him and the mouse, so I created one. This is the real Douglas Engelbart, and that's the real mouse. Now, there is a very famous research center in Palo Alto. Does anyone know what it's called? No? Maybe one? Yes, thank you. So Xerox PARC, right? Palo Alto Research Center, famous in the 70s and 80s for all sorts of computer technology that came out of PARC. Networking came out, object-oriented came out. And in fact, a young Steve Jobs went to PARC in the late 70s. He had a deal between Apple and Xerox. I don't remember the details. But he wanted to go and see what they're doing. And so he later in interviews, he says, okay, they showed him the Alto. And they showed him 3 things, but he only remembered 1. The 3 things they showed him, the graphical user interface with the mouse, networking, and object-oriented programming. That's 1979. He only remembered the mouse and the graphical user interface. And by the way, if you haven't caught on, that's not Steve Jobs. That's AI generated. And it's also not the Alto, because the Alto looks like this. And here you can actually see the mouse. But he understood. He went back to Apple, and he started the Lisa program, at the first commercial computer with a mouse and a graphical user interface. And yes, if you haven't caught on, that's not Steve Jobs. That's AI generated. But I could find a really good image of him. This is the Lisa with Steve Jobs. So this computer was a flop, a commercial flop. After that, he started the Macintosh. The Macintosh was somewhat successful, but it took 10 years. 10 years from 82 to 92 until computers were shipped with mice. Of course, Microsoft was sleeping through that whole episode. That's why it took longer. But the point I'm trying to make, Steve Jobs understood. The moment he saw the mouse and the computer interface, the user interface, he understood. That's how we're going to use computers from now on. It was a total paradigm shift from typing cryptic commands into a keyboard to pointing and clicking. And for me, this is a park moment precisely for this reason. What we're seeing with AI, I expect this to be a similar paradigm shift. Now we're moving from pointing and clicking to showing and telling. We train models and then we tell them what to do. So I have a couple of examples, right, that I did at home mostly, just to give you an idea. Some of this, you know, if you're a software engineer, you probably have done a lot more than I have ever done. But this is, I took one of our APIs and I put those through Bing Chat and I asked, hey, write me some code with this API. And Bing Chat did it, right? It wrote sort of a structure that you can use. It's not complete. It actually says, yeah, things are missing, but you can fill in the rest. This one is, I took one of our terminals, a Move 5000. I tried to embed it in Midjourney, and I just created a scene. So for content creation, this is actually going to be a big deal. Then this is also Bing Chat, created a website. I did not provide this text. I just said, here is the URL to a Move 5000 image. I want the image there, I want the text over there. Go do it. And I want the colors of WordLine. And it figured all that out. And that's quite astonishing. Then if you run Stable Diffusion, there's a thing called ControlNet that lets you do funny QR codes. These all work. That's Paris. It's always the same QR code, by the way. That's a waterfall. It's not very clear on the screen, but flower beds, jungle, another flower bed. So that's the fun part. And of course, power of plugins. And again, I use an example that I can visualize. So GPT-4 has now plugin support, right, for like 2 months. And what I've done is I've asked it first, okay, give me a prompt for a nice picture of Paris. And it gave me this. And Midjourney creates this. And it's okay. It's not what I wanted, really, but it's good. So I then asked, okay, I used this plugin in GPT-4, and I asked basically the same thing. And I got this. And you probably cannot see it well, but if you compare the two, so this is plugin, this is without plugin, the plugin version, much better. So that's, you know, prompt engineering through a plugin. Okay, just one final example here. This is Alpaca. I don't know if some of you may have experimented with this. Right? Stanford University had this great idea. We take a llama model, we create training data with GPT-3, and essentially we feed that data into llama and we create alpaca out of it. And this runs on my computer and I can ask it to do simple things. My point here is, well, I can run this at home on my computer. We should be able to do this too. Okay, sorry, I'm almost at the end, so don't worry. Bear with me. I just want to highlight a couple of things. March 23 will probably go into the history books. Very important things happened. Microsoft understood the significance. They announced we're going to bring everything into all the generative AI stuff into Microsoft Office suite. Of course, Google followed suit, right? Same story with Google. You can try out Bard today. You need a VPN because they have issues with the EU. But you can try it, and it's okay. It's not yet at the GPT-4 level. Of course, Midjourney version 5 came out, and it's really good. And now they're at version 5.2, and it gets better and better. So image creation is really good. Adobe came out with Firefly beta. I've been playing around with this since April, I think. And it's not there where Midjourney is, but it's quite good. And of course, GPT-4 was announced in March. And if you have a subscription, you can play around with this on ChatGPT. But GPT-4 is a big deal. It's a big deal because there was a Microsoft research team following the development of GPT-4, and they published a paper in, I think, April timeframe. And in the paper, they basically point out a couple of things, right? So first of all, GPT-4, as we know it, is very restricted. It's restricted for security reasons, because it also still hallucinates, but it's actually quite dangerous if we let it loose. The other thing is, can't read this, they asked it to solve problems, and it can actually do the reasoning and solve complex problems, and it can do abstract thinking. So it's quite far advanced. And that's why I think Microsoft never said it's multiple models, but they do say it's multi-model. So in a sense, the tweet I read last week that says it's actually 8 different models does sort of make sense when you read that. And finally, it's best with plugins and access to the internet, which is today severely limited because of security concerns. This is a quote from the research paper. So GPT-4 represents a paradigm shift in computer science, is what Microsoft found. So I leave you with this: the promised land, AI winters, or nuclear winters. And I have to refer to Hinton, because Geoffrey Hinton is very clear. He's very outspoken about this. He says there's an opportunity for us to reach the promised land, general intelligence. However, there's also an opportunity for another AI winter, because the brain uses 5 watts, right? We only need 5 watts to train ourselves to function. These models, they use the energy of small cities to properly function. That cannot scale. So we have to either find a different algorithm for all this and change it how it works, or we end up at a ceiling in another AI winter and we cannot go past that. He also gives nuclear winters a bit of a chance. If we skip right over AGI and end up in superintelligence, why not? Maybe we'll have Terminators running around. One thing is clear, because this story is 70 years in the making, it is now finally coming into the conscious minds. Right? We've been using AI, machine learning, on our mobile phones for 20 years, right? Even before. But now it actually started to make an impact in the masses. And that's why it's already changed the ways. And for me, it's the new computer mouse. So this is actually a real photo of Alan Turing. Maybe you recognize him. This is his test. Google and OpenAI both passed it. Thank you.